In this video, we will talk about absolute value equations. Let's start with the geometric definition of an absolute value. Geometric definition says that if you have absolute value of A, this means the distance from the origin or 0 to the point whose coordinate is A. So kind of giving you a mental picture here, if we have a number line and we have the origin here at 0 and we have, let's say, positive A right here, then the distance, this distance happens to be A, but we also have the opposite of A in this case, whose distance is also A. And so for that reason, that leads us to our theorem. And our theorem states if A is a positive real number and U is an algebraic expression, then we know this is true. The absolute value of U is equal to A is equivalent to U being equal to A and U being equal to the opposite of A. Because again, going back to that geometric definition of absolute value, since we know the absolute value of A is equal to, or the absolute value of U is equal to A, we know the distance from the origin, or in this case 0, is going to be A, and so the 2 points that satisfy that are going to be positive A and negative A. Using that definition and also that theorem, we are going to solve each of these and state the solutions in set notation. So again, think of this whole expression 2x plus 3 as U. We were saying the absolute value of U is equal to 5, so therefore U must be 5 and U must be also negative 5 because of the fact that the distance from 0 happens to be 5, and so the two values that satisfy that are 5 and negative 5 on our number line. Put back in our expression 2x plus 3, and now we have 2x plus 3 equal to 5 and negative 5. Now we can go ahead and solve these two linear equations. So we'll have 2x is equal to 2, and 2x is equal to negative 8, and so x is equal to negative 1, and finally x is equal to negative 4. So we do in fact have two solutions, negative 1 and negative 4, which when evaluated, meaning multiplied by 2 and added 3, will be a distance of 5 units away in the origin. Now set notation would have us write it opening a brace, 1 comma negative 4, and close a brace. Number 2 is a little different simply because I have a constant 6 on the outside of the absolute value. We have to first add or subtract the 6 to both sides. So in other words, we need to isolate the absolute value before we can actually use the theorem that we just stated. So we're going to subtract 6 to both sides so that we can get the absolute value by itself. So now we have absolute value of 1 minus 2z is equal to 3. And from here we can go ahead and split it up because 1 minus 2z is our u. This is equal to 3. So now we know u is equal to 3. U is equal to negative 3, and so substituting that expression back in, we know 1 minus 2z is equal to 3, and 1 minus 2z is equal to negative 3. Now as we go through the solving process of this, which I hope if you don't know how to do this, go back and look at the solving linear equations video. But if you don't know how, or if you, the one area that students struggle with is remembering to split this up into two different equations. Typically they'll write the first equation and they won't write the second. So let's go ahead and we subtract 1 to both sides. So we have 2z, negative 2z is equal to positive 2. And so z is equal to negative 1. We then have, for the second one, we have negative 2z is equal to negative 4, which means z is equal to positive 2. And the set builder notation for the solution will be negative 1, comma, positive 2. This last problem is very similar to the previous two problems, except that the expression on the inside of the absolute value is a quadratic, so we will have to keep that in mind. One quick note before I start this problem, let's say there, for example, there is a 2 coefficient on the outside of the absolute value. Never, ever, ever, under any circumstance, distribute that 2. It cannot be done and should not be done. Taking the absolute value is similar to doing an operation, and you can't multiply that 2 until you've completed that operation. So if by chance you were given a problem where there was a coefficient, you should divide both sides by 2. That will cancel this 2 out, and it will move it over to the other side of the equation, which will then give you a 1. So again, I changed the problem a little bit just to satisfy a quick note, but please make sure that when you have a coefficient, you are dividing both sides, not distributing. So the first thing I'm going to do, again, this u, absolute value of u, the u in this case is x squared plus 3x minus 2. Since it's equal to 2, we know u is equal to 2 and u is equal to negative 2. Substituting that back in, we have x squared plus 3x minus 2 is equal to 2. And x squared plus 3x minus 2 is equal to the opposite of 2, which is negative 2. All right, finally, what we have here is a quadratic equation for both of these, and we need to get these equal to 0. So x squared plus 3x minus 4 is equal to 0. I subtract 2 on that equation. And x squared plus 3x is equal to 0. I added 2 in that equation. All right, we will go ahead and factor these. So this will be x and x. We will have a plus and a minus, and so we will have positive 4 and negative 1. On this equation, we will have a GCF that we will have to factor out, which is x, which will leave us with x plus 3 is equal to 0. From here, we go ahead and solve the equation. So x plus 4 is equal to 0, x minus 1 is equal to 0, x is equal to 0, and x plus 3 is equal to 0. All right, so we know x is equal to negative 4, positive 1, 0, and negative 3. So our solution set in set notation will be negative 4, negative 3, 0, and 1. Personally, I like to list them in least to greatest order. I know I didn't do that in the last problem, but that's what I prefer to do.
Forget it.